So thank you very much. I'm Steve Hammond from the National Renewable Energy Laboratory in Golden, Colorado. And I want to thank you very much for inviting me to speak today. I regret that I'm unable to be with you in person. Our lab's approach to travel is evolving, but unfortunately not quickly enough to allow me to be in Houston with you today. You may be wondering about the title of my talk, Changing Aircraft Engines in Mid-Flight. I chose this title because the energy system that underlies our economy, our security, our relationship to the environment, and our daily lives is changing like never before. The changes to our energy system are akin to changing the engines on a plane mid-flight. You have to do it without disruption, and that's really important. Our energy infrastructure is rapidly evolving from an architecture of large centralized power generation and control to a hybrid system that incorporates a large number of distributed resources. At the same time, the power grid is becoming increasingly interdependent with other infrastructures like natural gas, transportation, water, and telecommunications. Although the challenges are significant, they also create enormous potential for innovation. So today in this talk, I'm going to focus on the challenges in energy transitions, large-scale deployment of renewables, vehicle electrification, community clean energy transition, sustainable materials, utility-scale hydrogen production, and how we're using advanced computing to help with this transition. Perhaps now more than ever, our ability to advance the leading edge of technologies is being driven by advanced computing. It's especially impactful at temporal and spatial scales, too small to directly manipulate, or in our investigation of whole integrated systems, too large and complex to manipulate through trial and error. We do a mix of computing here at NREL that includes exascale class problems and high throughput ensemble type computing. So my intent here is to give a flavor of the type and breadth of the work at NREL rather than a comprehensive coverage of all the work. It's interesting, today's my 20th anniversary at the lab, and we've gone, in that 20 years, we've gone from trying to do it at all. Can we produce electricity from
Steve, should your slides be moving?
Materials? Pardon me?
Should your slides be moving?
Not yet.
Okay, got it.
Yeah, don't worry. So in the 20 years at NREL, we've gone from trying to do it at all, generate electricity from PV and from wind, to now we're being asked to do it for all. I'll say a little bit about the lab. NREL is one of 17 laboratories in the DOE lab complex. As I said, we're located in Golden, Colorado, just west of Denver. We also have the Flatirons campus to our north with utility scale wind and solar and energy storage systems. And further north is our Cold Climate Housing Research Center located in Fairbanks, Alaska. We have about 3,000 employees. I think 4,000 of which have been added, 400 of which have been added since the pandemic started. So we have people who've never set foot on campus. We have about 2,000 regular staff, almost 500 contractors, postdocs, grad students, and undergraduates. One of the features of our lab is we really value partnerships. So we have approximately 1,000 partnerships with industry partners, academic, with universities and with government entities. The world-class research we do is more or less organized in disciplines, including renewable power, focus on solar, wind, water power, geothermal energy, to sustainable transportation, where we do research in bioenergy, vehicle technologies, hydrogen production, and end use and storage. Can't forget, we also do work in energy efficiency, because the sort of greenest electrons are the ones we don't need. So we look at building energy efficiency as well as advanced manufacturing technologies. Lastly, we have focus on integrated energy systems. So that's grid integration and hybrid systems. Much like a university at NREL, we're organized around disciplines and application areas. However, the work we do is actually very cross-discipline and multidisciplinary. It's integrated and cross-cutting. We logically group our work into 3 cross-cutting areas. This includes integrated energy pathways, where we try to optimize the integration of renewables with buildings, energy storage, and transportation. Our technologies don't sit in isolation. So one way to think about this is we focus on technologies and systems for the production and use of low-cost, sustainable electricity. In Electrons Molecules, also referred to as power to X, we look at the conversion of electricity and small waste gases into chemical bonds for the purposes of chemical, material, or fuel synthesis. Last, there's circular economy, where we look to advance the fundamental knowledge and technology for design, recycle, reuse, remanufacture, and reliability for material and processes. We want to consider the full life cycle of these products and materials from cradle to grave. It would sort of defeat the purpose of our focus was solely on sustainable energy, but we did not take into account the life cycle of materials needed. The last thing we want is to have landfills overflowing with old wind turbine blades. The current administration has set aggressive targets that will fundamentally change our energy system. These are to be carbon-free in our electricity sector by 2035, and overall have net zero greenhouse gas emissions by 2050. According to a 2021 International Energy Agency report, a roadmap for the global energy sector, all the technologies we need to achieve carbon-free US electricity generation by 2035 exist, and the policies to drive their deployment are already proven. The good news is that in many areas, wind and solar energy are already the cheapest sources of electricity. The 2050 goal is a bit more challenging. Reaching net zero greenhouse gas emissions by 2050 requires further rapid deployment of available technologies, as well as widespread use of technologies that are not yet on the market. Major innovation efforts must occur over the next decade or so in order to bring these technologies to market in time. Heading towards 2050, almost half the reductions will need to come from technologies that are currently only at the demonstration or prototype phase. In heavy industry and long-distance transport, the share of emissions of reductions from technology that are still under development is even higher. This graphic illustrates the US electricity generation by fuel source from 2019. You can see on the right that fossil fuels provided about 60% of our electricity, and clean energy sources provided about 40% of the total electricity supply. At the far right, you can see wind and solar together account for about 10% of our current electrical supply. To meet the 2035 goal, just focusing on wind and solar alone, we would need an annual addition of new wind and solar capability, roughly equivalent to half of the installed wind and solar base. So just to do the math, if wind and solar is 10%, half of that is 5%, and if we added 5%, the equivalent of 5% of what we've done each year for the next 12, that's how we get to the 60% that's currently supplied with fossil fuels. The challenge is thus to integrate large amounts of wind and solar energy into the power grid while maintaining security, reliability, and enhancing resilience. It's doable, but I think it's a little daunting to think about. The good news is that annually new installations of wind and solar are already the largest new additions of electricity generation to the US grid. Lots of reasons for optimism. In solar, there's been dramatic improvements in the cost, efficiency, lifetimes and manufacturability of PV materials. Similarly, in wind, offshore wind turbines are now looking at in excess of 10 megawatts per turbine. Plant level control strategies are showing that we can improve the yield approximately 10% through better control of individual turbines and coordinated wind plant controls. So this is both for improving the output of existing fleet and for improved siting and operations for wind plants to come. Wind energy is poised to play a significant role in the future energy system. Let me start with a bit about wind energy research at the lab. First, a little background. So the wind energy capture potential of a wind turbine is proportional to the swept area of the blades. Thus, taller turbines and larger rotors provide greater energy capture potential of wind resources and help lower the cost of wind energy. The length of the blades for land-based systems is constrained by highway turning radius because those are largely moved along our highway system. Also, the diameter of the towers themselves are constrained by bridge clearances. Offshore wind installations often don't encounter these constraints, and thus offshore turbines are now in the 10 to 20 megawatt range for a single turbine. Wind energy research challenges include how we advance offshore wind with technological innovations, such as floating platforms and scaling solutions for larger turbine designs, advanced turbine controls, and lighter weight materials for drivetrains. We're also looking to foster turbine designs, advanced turbine controls, and lightweight foster sustainable and circular economy by developing advanced wind turbine and component materials, methods for improving recyclability and recovery. Lastly, we want to validate multiple wind technologies at scale to achieve integrated energy systems that meet the complex energy needs of the future. So Mike Sprague is the PI of the ExaWind project. Many of you may have heard of that. It's part of the exascale computing project within DOE. This represents a significant investment in wind energy simulations. The project itself started in 2016. It's an interesting project in that the DOE Wind Office is funding the focus on high fidelity modeling in partnership with NREL and Sandia National Laboratory to ensure that the wind code addresses wind relevant problems and that the models are validated. The exascale computing project from the Office of Science is making sure that the codes are performance portable and will run well on next generation supercomputers. The ExaWind project is a very robust partnership with NREL, Sandia National Lab, Oak Ridge National Lab, and the University of Texas at Austin. The ExaWind code is based on Nalu wind from Sandia. It's an incompressible flow computational fluid dynamics code, features unstructured grid, infinite volume discretizations. It's closely tied to the numerical libraries Tolinos and Hyper, and incorporates both blade resolved fluid solid structure interactions as well as actuator type simulations. The ExaWind code aims to be the highest fidelity model to power wind plant simulations to date. ExaWind runs on a variety of HPC systems, including the Summit supercomputer at Oak Ridge National Lab, one of the world's fastest systems. The resulting high fidelity models will enable a great leap in our understanding of and the ability to predict complex flows and turbine responses within wind farms. Widespread deployment of wind energy to meet the 2035 goal will require that wind farms be composed to megawatt scale turbines. This will be both land-based and offshore. If you think about the scales of the dynamics, they span many orders of magnitude. And it's a coupled complex system that incorporates weather effects, mesoscale processes such as clouds and convection. There's also intra-plant features, which is focused on turbine-turbine interactions and the dynamics of individual turbines. So the focus here is to accurately model the wind system so that we can optimize the power production. So we want to maximize the energy extraction from wind and maximize turbine life and minimize disruptions. A DOE report from a few years ago concluded that the primary way to reduce the levelized costs of electricity from wind was to improve the wind plant dynamics, including better understanding of turbine-turbine interactions. This was as opposed to investing in further improvements in individual turbines. With ExaWind, we now have the high power tool for that purpose. From a validation standpoint, we've been able to use the ExaWind code and for the first time reproduce experimental results done in the 1990s in the NASA Ames 80 by 120 wind tunnel. Like boats, wind turbines have wakes that create coherent turbulent structures that persist far into the interior flow field of a wind plant. So we're using the ExaWind code to study wake formation, meandering, and wake dissipation to fully understand the impacts of these turbine-turbine interactions. We've learned that it's possible to adjust the pitch and yaw of upwind turbines in ways that effectively steer the wake away from downwind turbines. This makes a small reduction in the energy capture or the energy production of the upwind turbines, but overall it optimizes the energy efficiency and the energy production of the wind plant, often by as much as 10%. Also, by reducing the turbulence that's shown in these two diagrams here, experienced by the interior plant turbines, it reduces the material fatigue suffered as a result of being in turbulent flow and improves plant reliability and reduces maintenance costs. In addition to work on supplying renewable energy to the grid, we're investigating ways of managing electrical loads on the grid itself. This includes building loads and electric vehicle charging. Part of the challenge is that uncontrolled or uncoordinated EV charging could cause large spikes in load on the grid that are costly or hard to manage. These types of loads were never anticipated when the grid was designed. So we've created digital twins of community vehicle behaviors and EV charging rates to test the development of control strategies for coordinated vehicle charging. So it's possible to shape, shift, and shed demand for electricity from the grid without sacrificing vehicle charging needs. So we show in the graphs below, the orange would be unconstrained charging. If, for example, in a community, people arrive at work and they plug in electric vehicles, but this would be a large spike in charging demand if simply everybody's vehicle started charging at its full capacity all at or near the similar time. So we look for ways to coordinate the charging of vehicles, because it's clear not everybody would need to be fully charged instantaneously, in ways that we can use AI and machine learning, look ahead to vehicle charging needs, building demands, and coordinate that, and maybe delay the rate of charging for vehicles if people are going to be in the office for a while and don't need immediate charging. So we also look at ways of doing on-site storage, which might cost a bit more to provide on-site storage to reduce grid demand, but it has a more increased effect in reducing instantaneous loads on the grid. Also, if multiple buildings and community level trading was done, vehicles could coordinate across broader areas and help further reduce, but that may not need vehicle energy storage within the buildings for vehicle charging. Hydrogen is interesting in that it's poised to play a critical role in future clean energy economy, particularly in areas where direct vehicle electrification is challenging and harder to abate sectors such as steel, chemicals, long-haul transport, shipping, and aviation. Some of the research challenges come from the fact that the cost of green hydrogen production is currently a major barrier to its uptake. Most hydrogen today is produced using steam methane reforming of natural gas, and it costs about $2 a kilogram. Most of that cost is the cost of the natural gas itself. Through the Department of Energy, they've launched the DOE Hydrogen Shot as an initiative to focus on 1-1-1 goal. They want to produce 1 kilogram of hydrogen at $1 within 1 decade. If we can achieve this goal, it would be a game changer for both industrial uses as well as for seasonal energy storage. One of the things we're doing at NREL is looking to, as part of our hydrogen research, is creating a hydrogen scenario analysis modeling capability for developing high-resolution insights into future optimized green hydrogen pathways. So we're looking to develop a national roadmap, somewhat like you would have with seismic for oil and gas exploration, of where hydrogen might be produced effectively and at low cost, and a blueprint at each installation that will allow us to achieve DOE's 1-1-1 goal. So we're using very high spatial and temporal fidelity wind and solar resource data sets that we can then feed into models, plus looking at policy scenarios and anticipated technology costs to develop optimized hybrid energy systems for hydrogen production. So these would be purpose-built systems. and the costs across the US, both on and off grid scenarios. And we're looking at a decade's worth of analysis starting in 2025 up to 2035. So the H2OP analysis tool takes advantage of these high-resolution data sets. And the idea is to take DC power directly from wind turbines or solar arrays, or coupled with energy storage such as batteries, and drive electrolyzers with minimum losses with specific power electronics, reducing AC-DC conversions, and based on location-specific resources to size the wind portion and the solar portion to support the lowest cost hydrogen production. This is a significant computing challenge because it accounts for daily and seasonal variability in wind and solar resources throughout the US for optimal design. And again, we want to demonstrate the cost trade-offs between off-grid and on-grid with low-cost power to cost-effectively build in remote locations without transmission. Electrolyzers themselves use electricity to split water into hydrogen and oxygen, and they can take DC power at variable power levels. So we're looking at optimized design, sizing of components, and the impact will be different designs are required for different objectives, different end-use markets, and different locations. And the analysis will combine technology, cost, policy configuration in near real time at very fine spatial resolutions. So using this tool, we have some preliminary results, and the computational analysis makes it possible to produce maps like this, showing potential costs for producing hydrogen. In this particular scenario, in the 2035 timeframe, the assumptions were that it included the production tax credits. In this scenario, it was wind only, no storage, no solar, and it was off-grid, so it was not dependent on grid. And this shows that through the midsection of the US, it would be possible to build wind-based hydrogen production facilities that produce hydrogen at a cost of $2 or less per kilogram, and in many places, reaching that $1 a kilogram target. This is important as we look to develop pathways to decarbonize major industrial sectors such as steel production. There are emerging technologies for steel production that use hydrogen to dramatically reduce greenhouse gas emissions. Also, I show a map in the lower right of steel production locations in the US, and it's promising to see that there's a good correlation in the US between where hydrogen can be produced cost effectively to align with current steel production locations. Sustainable materials is another active area of research at NREL. One of the challenges we face is the sheer longevity of plastics, and thus our interest in sustainable materials. We're looking to find alternatives to current plastics that meet product performance requirements, but with much less impact on the environment, both in their production and how they end up. So the material design space is vast, and a trial and error approach is inefficient. So we're using high performance computing and high throughput machine learning techniques to start from millions of possible polymers to down select and identify materials with desired performance characteristics. So we're looking at performance advanced bioproducts that are candidates for new plastic uses. So we generate lists of potential candidates. We can down select to a few hundred. We can then do detailed analysis of those to select maybe order 5 to 10 that would be synthesized. So in a particular case study, we're looking at bioadvantaged PET substitutes. PET is the most common material from the polyester family used in fabrics, films, bottles, and improved thermal and barrier properties that would expand the application space of these bioproducts. So using our machine learning, we started with order millions of possible. We screened 15,000 polyesters. We've identified 5 potential targets that are currently being synthesized. And all of this was driven with molecular dynamic simulations for investigating structure-function relationships. addition to helping advance renewable energy technologies, we also worry about their security and resilience. NREL's work in the energy security and resilience sector is a direct extension of our work and expertise in the design and operation of clean, highly distributed energy systems. The research challenges we face are to understand disruptions and minimize impacts from natural and human threats to critical US infrastructure. We're also looking to develop AI techniques for intrusion detection, cyber and physical attack recognition, and forensics, all reflecting real-world scenarios. This is evolving condition monitoring techniques or anomaly detection from improved operation to detecting off-normal operations that would indicate perhaps someone with nefarious intent. So renewable energy technologies encompass large and diverse number of devices, including wind, solar, hydropower, and marine hydrokinetics. Quite often, these technologies are aggregated into hybrid systems functioning as single operational renewable energy plants. These renewable energy technologies comprise the fastest growing portion of our electric grid and are increasingly internet and grid connected. However, while renewable energy systems offer a promising path to future, the sheer number of these devices and their interconnectedness greatly expand the vulnerability and opportunities for disruption. Our work in the area includes novel physics-based digital twin methodologies, which are again computationally intensive for state estimation. We combine these with machine learning techniques for anomaly detection and analysis of streaming weather and LiDAR operational data. Together, that gives us a view of, if we know the inflow conditions and we know operating conditions, we can look at what we would expect a plant to perform, and we look at its actual performance and do that to ensure the security and resilience performance and that's not being compromised. Let me say a few words about a newer effort at NREL called ARIES, our focus on advanced research in integrated energy systems. ARIES is a platform at NREL supported by DOE's Office of Energy Efficiency and Renewable Energy. It'll support our nation's transition to a decarbonized energy system. It provides a safe proving ground that will allow us to introduce and significantly reduce risk and vulnerability at the expense of utilities and electric grid and customers. So I'm showing the two components of ARIES. So up top is the Energy System Integration Facility, where we do order megawatt scale experiment and development effort. And lower is our Flatirons campus, just north of our Golden facility, where we have a handful of utility scale wind turbines, utility scale PV arrays, utility scale, megawatt scale battery storage, all interconnected, which allows us to deploy and work with these to reduce the risk with utility partnerships. So the ARIES platform features the 20 megawatt scale microgrid, as well as the 2 megawatt scale ESIF, all complemented with a virtual emulation environment. So the experiments that we do with utility scale individual devices can then be aggregated into a virtual environment to study leading edge future complex energy systems. So that the ARIES platform will make it possible to understand the impact and get the most value from millions of new devices that are being introduced to the grid, such as electric vehicle charging, renewable energy generation, hydrogen storage, all being connected to the grid daily. At NREL, we are developing our efforts in new partnerships is very important. And we sort of have this notion that if we want to go fast, we can go alone, but if we want to go further, we want to work together. So we're working closely with industry partners to ensure that the innovations that are deployed into the marketplace, and this is best done through our direct collaboration. As I mentioned earlier, NREL has extensive partnerships with more than 1,000 active partnerships across industry, academia, and governments. In 2021 alone, we had 336 new partnership agreements. 323 new unique partnerships were developed And we have 714 active partnerships. So these partnerships take a variety of forms. In diverse technologies, we're working with the Southern Company to meet needs of future energy systems, including scaling of physical devices, controlling large numbers of diverse devices, and integrating these into the grid. On the advanced control side, we're working with companies like Eaton, Nextera, GE to demonstrate control strategies, autonomous energy systems, advanced storage, and renewable energy system generation. In the electrons and molecules area, we have partnerships with Princeton University and Shell to develop gas diffusion for electrodes on how hollow fiber membranes can be used to generate tunable ratios of CO2 and hydrogen from CO2, and to help with the genetic engineering of cyanobacteria to maximize the production of isopropanol. In sustainable methane, we're working with SoCalGas and Electrochia to demonstrate electrolysis of water in combination with biological production of pipeline quality methane from hydrogen and captured CO2. In the area of circular economy, as I said, we have a significant focus on biomaterials. We're exploring chemical, biological, and enzymatic strategies for other plastic degradation. And we're looking to complete the synthesis of novel PET-based water bottles and their equivalents that are capable of degrading much, much faster. We have a partnership with ExxonMobil and Apple regarding the general plastics upcycling and applications for industrial polymer end uses. A couple of partnerships I'd also like to highlight. We have a project called Athena with Dallas-Fort Worth Airport, helping researchers working with Dallas-Fort Worth planning to provide transportation hubs with decision support and actionable insight. So the Athena project leverages our HPC capabilities and digital twins that we developed to model current and future scenarios for the airport itself. DFW is one of the world's largest airports, and their focus is to achieve carbon neutral status. So we're working with them on shuttle bus electrification and routing and electrified baggage and freight movement. We also had the LA 100 project where we partnered with the city of Los Angeles to determine investment needs to achieve the goal of 100% renewable energy by 2045. Through the LA 100 study, we provided data, advanced computing, analytics, and expertise to provide them with decision support in assessing and planning the pathway to meet their target. These cutting-edge insights will help the Los Angeles Department of Power and Water to chart its path forward. So with that, I think I'll wrap up. Again, I regret that I'm not able to be there with you in person, but I want to thank you for inviting me, and I'm happy to answer any questions you might have.
Steve, I have a question for you. You mentioned all these partnerships. How does one start a partnership with you?
Just contact somebody at the lab. I mean, it's easy for somebody to, contact me, for example. I think my email is accessible through here. I'm happy to make the connections depending on the interests. So I think that's probably a good start. And what I tried to do is give a sample of the kinds of work that we do. So if there's something of interest, I'm happy to be a point of contact.